like that, okay? Now, on the next page then, you had 4.5 here, where you had arrow and box diagrams. So they have 1s, 2s, 2px, 2py, and 2pz, okay? And they have that, and then you're asked to draw the electrons. So they've boron done for you, so now you have to do carbon, okay? 6 electrons. So 2 electrons go into the 1s, okay? 2 electrons can go into the 2s orbital. Now, remember Hund's rule of maximum multiplicity, that when 2 or more orbitals of equal energy are available. Now, you have 3 orbitals here, and they all have equal energy. So when they're available, you have to fill them singly first, and then come back and put the electrons in pairs. So you have to go 1, 1 there for carbon. Okay, now just double check that I have the right numbers of electrons in. 1, 2, 3, 4, 5, 6. Okay, that's carbon. Now, then they asked you, oops, sorry, one second now, and I'll just rub out carbon here. Oopsie, I'll just rub out carbon here. Then they asked you to draw nitrogen, okay? So nitrogen has 7 electrons, so you go like that, but you'd have to put the last electron in there like that. And then finally, they asked you for oxygen. Oxygen has 8 electrons, okay? Now, where will you put the 8th electron? Into your 2px, okay? And remember, Pauli's exclusion principle stated that no more than 2 electrons can go into an orbital. That's one orbital here. So you can only have 2 electrons, and they have to have opposite spin. Okay, so name and state the rule that's illustrated. That would be Hund's rule, because you're filling them singly and then you're coming back and filling them in pairs. Atomic number 21, then they asked you to write the configuration. That's SC, so you're just writing 2p6, 3s2, 3p6, 4s2, and then finally 3d1 there for the last part, okay? Now, the last question then, stating Pauli's exclusion principle. Well, I stated that earlier on there, where no more than 2 electrons can occupy an orbital and they have to have opposite spin. Then you were asked to name the following structures, okay? So that would be similar to what I was doing there earlier. So you'd add up the number of, oops, sorry, that's 3. Add up the number of electrons. And when you do that there, look, so 2 and 2 is 4 and 6, 10, 12, 18, 20, so 28. Then you go to your periodic table. What has an atomic number of 28? And you'll see that it's nickel, Ni. The second example then, it's an ion. The reason you know that it's an ion, because it's got a charge. Okay, the top one didn't have a charge, that's just an atom. It's a -2 ion. Count them up. 2 and 2 is 4 and 6 is 10, 12. So you have 18 electrons in the ion. Now, it's a -2 ion. So what happened to the atom that formed that ion? It gained 2 electrons, didn't it? Because it's -2, so the atom gained 2 electrons. So originally, the atom had 16 electrons. Now, go to your periodic table. What has an atomic number of 16? Sulfur. So when you're identifying that ion there, it's S-2 is your answer. Then you're asked about an isotope, defining an isotope. That should be fine. And then it asks you about copper, okay, 29, and, oops, sorry, and what was the other one? 65 and 29. And then how many protons and neutrons are in these isotopes? So isotopes, atoms of the same element, but they have a different mass number due to different numbers of neutrons. So they both have 29 protons, so because the atomic number is the same, atomic number is 29. But by subtraction, for the first copper, there, you're getting 34. And when you subtract 29 from that, what you're getting? 36. So there's different numbers of neutrons, okay? And then in the next part there, look, you were asked to find the relative atomic mass. 70%, okay, is copper 63. 30% of it was copper 65. So 70 times 63, you need to calculate that. 70 times that. Now, when you calculate 63 times 70, you're getting 4410, okay, and then 30 times 65, okay, gives you that. So when you toss that up then, you're going to get 6360, but that's for 100 atoms. So divide that by 100. What would one atom be? Okay, atomic mass unit. All right, so that's how you'd work out relative atomic masses like that. Now, the maximum number that can be accommodated now, n equals 3. That's your main energy level. It's made up of 3 sub-levels, 3s, 3p, and 3d. We said that you can put 2 electrons into that, 6 electrons in here, and 10 electrons in here. So in total, you can put 18 electrons into the third energy level. There's a formula that will help you actually. that we haven't really met because it's more in chapter 3, but I may as well introduce it here. 2n to be squared, where n is equal to the level, the number of the level. So if it was the 4th main energy level, then you put in 2, okay, 4 there to be squared. So 4 to be squared is 16. 16 times 2, then you're going to get 32. So you can actually put 32 electrons in the 4th main energy level. 18 is your answer there, that you can put into the 3rd main energy level. Now, for potassium, if you can put 18 electrons into the 3rd energy level, why isn't potassium's configuration like that? Potassium has 18 electrons. So like, why don't you put 2 into the first shell, 8 into the second shell, and 9 into the third shell? Wouldn't that add up to 18? 2 and 8 is 10 and 9. But in fact, when you're writing the configuration of potassium, like when you were in second year, you wrote it like that. Why did you write it like that? Because yes, there are 2 electrons in the first shell. There are 8 in the second, because you can put in 2 into the 2s and 6 into the 2p. So 2 and 8 and 6 gives you 8 electrons there. 8 in the third, because it's 3s2 and 3p6. That's your 8 there. And 4s, remember. So you're putting the 1 electron there, then into the 4s. So remember that because the 4s sublevel is lower energy than 3D, you fill the 4s before you would start to put electrons into 3D. So that's why the configuration looks more like that than that. That's not correct. So the 4th, after you've put 8 electrons into the 3, the 3rd level, 4s is lower energy than 3D, so the electrons go in there before you put them into the 3rd. Okay, great, thank you.